This is going to be a short presentation on the main equations from Chapter 15 about fluid. Fluid dynamics is based on Bernoulli's equation, which you see written out here, plus the continuity equation specialized to the case when you've got an incompressible fluid. We'll see this detail in a few moments. First, I want to just point out to you that several of the terms in Bernoulli's equation look just like conservation of energy terms, with the mass replaced by the density rho. This is not an accident. Bernoulli's equation is an equation about energy conservation per unit volume. So it ends up having a number of terms that are very familiar to us, and it's used in the same way that we've used things before. The conditions here, first of all, require steady flow. Irrotational means there's no rotation, no turbulence in the fluid. Under those conditions, we can define a flow tube where the fluid speed is the same at any particular point within some small region of the fluid. This is called a flow tube because it's sort of, you can follow the streamlines of the fluid from one point to another, and they define a little sort of conserved region there where the fluid is flowing. But if the fluid is compressible, the density might change. What's conserved is the mass. So density times the volume, that is density at 1 times the volume per second. That's what A1V1 is. Volume per second times the density is a mass per second. So the mass per second flowing into the region must equal the mass per second flowing out of the region. If the fluid's not compressible, we can do a little bit more. For our ideal fluid that we talk about here, which is inviscid, has no viscosity, and is incompressible, if it's incompressible, that means the density cancels out of the continuity equation. It's just going to be A1V1 equals A2V2, which you saw in that first graph that I put up. No viscosity gets rid of another problem. Laminar flow, which is shown on page 257 of the textbook, means that the velocity profile is not constant all the way across a pipe. But if you have no viscosity, you won't have that problem. The fluid won't have any friction with the surface. It flows completely freely, and you can say that A1V1 is equal to A2V2 across the entire area of the pipe or hose. And again, you don't have to break it up into little flow tubes, each of which has the same velocity, because the velocity profile is completely flat. Finally, that incompressible aspect of an ideal fluid means the volume is constant. And in particular, no energy goes into compressing the fluid, just as no energy goes into producing turbulence. That aspect is really important because this equation is about energy conservation. Bernoulli's equation can be applied to water if we're careful. We have to be in a case where we can ignore the problems caused by laminar flow. But it's only an approximation for a gas like air. It really only applies at subsonic speeds where there's no shock waves forming. That is where the fluid is actually being compressed during the process. As long as the fluid is moving sort of smoothly without turbulence or shock wave formation, we can use it as an approximation for gas flow. But that's an extremely limiting case. That doesn't apply to aircraft, especially supersonic aircraft, where you have to be a completely different approach to those problems. Anyway, Bernoulli's equation is just energy per unit volume. And if we look at our standard conservation of energy equation, K plus U, K naught plus U naught plus the work, per volume, you can immediately identify that when you divide the kinetic energy by a volume, you get M over V, which is just the density. So 1/2 rho V squared is just kinetic energy per unit volume. Similarly, when you divide mgy by the volume, you get M over V, which is rho. So rho gy is just the potential energy per volume. So those two terms are completely familiar to us, just turning M into rho. The one that's tricky is the work. Work is, of course, going to be force times distance, where the force would be pressure times area. So the work done at one particular point in the fluid is the initial pressure, say P naught times the area A naught, so that's a force at position 0, times the displacement at position 0, that would be the force applied to the work done on one side, minus the work done on the other side. Divide that by the volume, though. A times delta X is constant, because that is just the volume of the fluid, which is preserved because of the continuity equation. So that term just drops out and becomes P naught minus P. So that's how you get Bernoulli's equation. If you want to see that slower in more detail, you should look in the textbook. This screen, you might want to pause the video for a second and look it over, because this is how we do problems with Bernoulli. We just write out the two sides of the expression. identifying everything with a 1 on it at one particular point in the picture and everything with a 2 on it with another particular point. In addition, we use the incompressibility formula to relate velocity and area. So for example, if we know the V1 and A1 and we know A2 is bigger, we can calculate that V2 will be smaller. So the incoming kinetic energy is larger than the outgoing kinetic energy just because the area got bigger. In addition, there's a potential energy here. There's an mgy, I should say rho g y1 and a rho g y2. At y2, at point 2, the potential energy is larger. So there's less kinetic energy but more potential energy. It's possible that those exactly balance, but more likely the pressure is different. So what is sort of different about this compared to things we've done before is that you get a trade-off between 3 different quantities: pressure, kinetic energy per unit volume, and potential energy per unit volume, where the rest of it's just bookkeeping. Like when we did conservation of energy problems, we just have to write down the equation, figure out which ones we know, see if anything's the same on both sides of the equation and cancel those out. Otherwise, we just have to sort things out and plug in the numbers, where usually rho is 10 to the third, that is 1,000 kilograms per cubic meter if it's water, but sometimes it's air where the density of air is approximately 1, actually about 1.3 kilograms per cubic meter. So that's the end of this. The pictures are all taken from chapter 15 in our textbook.